Hello, this is the start of chapter 9, which is talking about dislocations and strengthening mechanisms. Here, by having knowledge of dislocation and knowing the role that dislocation play in the plastic deformation process, then we are able to understand mechanisms and techniques that strengthen and harden metals and their alloys, of course, and therefore we go one step ahead towards design and tailoring mechanical properties of materials. Here we talk about why are the number of dislocations present greatest in metals. We'll talk about how are strength and dislocation motion related, and we say why does heating alter strength and other properties. In metals, say copper or aluminum, we are dealing with pool of electrons, and ions are actually in this pool. Therefore, dislocation motion is easiest in metals. We have non-directional bonding, so there is no preferred directional bonding, and there are different close pack directions for slip. When we move to ceramics, mostly ceramics like silicon or diamond, we see mostly like covalent bonds. Of course, motion for dislocations are harder, is difficult, and we have directional or angular bonding. In ionic ceramic like NaCl, the motion, of course, is again difficult. Here, for a dislocation to pass through the material, it needs to avoid nearest neighbors of like sign. Say if it's positive, it has to avoid from positive sign or from the negative if it is negative. As we discussed in chapter 6, in metals, specifically plastic, deformation occurs by slip. As shown here, and a slip dislocation, an edge dislocation, which is an extra half plane of atoms like this one, slides over adjacent plane, so it goes from, say, due to this shear stress applying from left to right, it goes from left to right, so it slides over adjacent plane and make a new half plane which is to the right of the previous one, and finally we see a permanent deformation, what we know as plastic deformation. Of course, if dislocations can't move, then we don't have plastic deformation. Remember, if we apply linear or plastic deformation to a material and then I unload the material, we are hardening the metal. Just to correct myself, by material in the previous sentence I mean metals. The motion of edge dislocation is also shown here. For dislocation motion, we require successive bumping from of course of the half plane half plane of atoms from left to right here, as shown in this picture. As you can see, also these bonds, the half plane go toward the right, this bond is broken, and another new bond is remade between this one and the green one. Now we have a half plane here, so on and so forth until the half plane reaches to the right and we have permanent deformation or plastic deformation. In which direction dislocation moves? It moves along a slip plane in a slip direction. As you can see, this is the slip direction, and it is perpendicular to the dislocation line. This one is the dislocation line, and we see you see the motion direction is perpendicular to this line, which is the slip direction. In skewed dislocation, you also see dislocation moves towards this pink arrow, which is again perpendicular to the slip direction, and we see the whole movement is along the slip plane from right to left. But where do these dislocation or deformation take place? This deformation takes place along slip planes in or towards slip direction. By slip plane, we mean a plane in which easiest slippage occur. So in these planes we have highest planar densities and of course large interplanar spacing. And by slip directions we mean direction of movement. Of course in this direction or along this direction we have highest linear densities, and you know, by linear density we mean the number of atoms along a certain direction, as we discussed it in the previous chapters. As an example, in FCC crystal structure, slip occurs on 1-1 planes. Of course, you know, 1-1 planes are slip planes. They have the highest density, planar density, of course, and in each plane it happens along a line or direction that we have highest density, highest linear density. Of course, for this plane this happens along this direction, which is 110, 110, and the same. So based on this picture, total of number of slip planes or slip system in FCC can be found. I've also made this model in SolidWorks. Yeah, this one here. Assume that we are dealing with crystal here, and I have shown two of 1-1 plane here. One is starting from this corner, ending to this corner and this corner, and the second one is this one, and this one. So these are two slip plane, and in each of them we have 3 directions. So based on this you can easily find the answer to this question, the number of slip system in FCC. Of course, for BCC and HCP, there are other slip systems. Bear in mind that all is a slip and deformation is caused by shear along a certain direction. Now here we want to find the relation between stress and normal stress applied to a material and the shear stress along a certain direction, along the slip direction. As you remember, normal stress can be defined by force divided by initial value of area. If we resolve this, the value of stress into 2 components, one of them normal to this direction and the other one along this direction, this one is actually the same value of shear stress, the value or the shear stress or resolved shear stress that we are looking for. Shear stress is equal to the shear force divided by this area along the slip direction. Now if I want to find the relation between the resolved shear stress, this value here, and the applied tensile stress sigma here, I have to find the relation between shear force and applied force and the slip plane area and the normal cross-sectional area. This can be found from here. Fs is, as you can see from here, it can be resolved from force F. If the angle of this plane and force is gamma, then of course Fs is F cosine gamma, and the value of As or area along slip plane or along slip direction is equal to the initial value of A divided by cosine phi, in which phi is the angle between the normal to the initial cross-sectional area and the normal to the slip plane. So if this angle is phi, then the value of As is equal to A divided by cosine phi. So using these two relations, we can simplify it, the whole relation, and find the relation between resolved shear stress tau r and applied stress sigma, which is related to cosine gamma and cosine phi, and the definition of gamma and phi are shown here. And this value, the multiplication of cosine gamma to cosine phi, is called the Schmidt factor. Bear in mind that the angle between two vectors, one having elements of u1, v1, w1, the second having elements of u2, v2, w2, can be found using this relation. The value or the shear stress value at which the slip plane happens is known as, or is named as, critical result shear stress. Of course, the condition for a dislocation to move then gonna be the resolved shear stress to be bigger than or equal the critical shear stress. Of course, based on this relation, the ease of dislocation motion of course depends on the angle or orientation of crystallographic orientation. If you have a look at this example, you see normal stress is applying along this axis and say y-axis, and shear stress is applying on this plane along x-axis. Gamma is equal to 90, therefore tau r is equal to 0. If we change the angle of this plane to 45 degree, then gamma gonna be 45, phi gonna be 45, and tau r gonna be phi sigma over 2. And if we rotate another 45 degree, we see the resolved shear stress gonna be 0. So we see a maximum point at angle of 45 degree shown here. The value of critical result shear stress is between these two in general. Now let's solve this question. We are dealing with a PCC crystal which is subjected to a stress along this direction. We want to find the shear stress on this plane along this direction when the tensile stress is 100 megapascal. Of course, in order to find the angle of gamma and phi, we have to use this relation. We can work it out in the class. For a single crystal that is under stress, deformation is as shown here. The slip occurs along a number of equivalent and of course most favorably oriented planes and direction at various positions. So that's why you can see these steps are showing on the surface of the material which is under tension. Another example, we want to find and figure out whether in this single crystal which is under a stress of 45 megapascal, and we have angle of phi and gamma, and this is the critical resolved shear stress, will the single crystal yield or no? So what we do, we use the relation in order to find the resolved stress. We have cosine phi, cosine gamma, and we have the value of sigma. Of course, if we plug these values into this relation, we have the value of tau equal to 18.4. Since this value is smaller than the critical resolved shear stress, then of course this single crystal will not yield. Now we go to the second part. It says, okay, if it doesn't yield, then at what stress it will yield? Of course, we should have a value of sigma which provide the value of 20.7, so we can write down the equation again like this one, 20.7, and the value of sigma is now not known. We have the value of sigma y and sigma phi from the previous one, knowing the angles as shown here. Therefore, the value of sigma that results in yielding is equal to 50.5 megapascal for this specific problem. Okay, this is the end of this session. Thank you.